Hi everyone, this is Andres Espinosa from the University of Maine. I work with Luis Zambrano Cruzati and Dr. Aaron Galand in modeling of soil carbonation for sustainable soil subgrade stabilization. I will talk about this project from the motivation, the collapse of subgrade soils due to freeze and thaw. We are all familiar with these. I am showing this in figure number 1 on the left. Is basically the holes in the pavement or the roads. And this is a consequence of the changes on the temperature during the year. Basically, these changes on temperature create changes on volume of the soil, and it makes the soil to collapse. There are out there different methods or treatment of soils. However, these methods have a high footprint. So we all know that right now we have to focus on strategies on how to reduce the CO2 emissions to the atmosphere. And then soil carbonation can do both. It can improve the soil, it can increase the strength and the stiffness on the soil, but also it can reduce the CO2 that is being emitted to the atmosphere. So how does it work? Basically taking the CO2 into the subgrade. We inject the CO2 and it will react with lime and it will create some minerals that will attach the particle together and make it stronger and stiffer. For more understanding about the reaction, I will take an element of soil, and then if I place lime on the voids, I will focus on the voids. And if we take lime and water into those voids, we will inject CO2, it will react, it will create an exothermic reaction, and then it will create the binder. This binder is calcium carbonate, and this calcium carbonate is the one that is attaching the particles and making the soil to be stiffer and stronger. All right, so having the understanding, we have evidence of this method. It can work for making the soil stiffer and stronger. And then it is important to know how this works. And for this is useful the modeling and try to approach it to be useful in the future for different projects. All right. So for modeling soil carbonation, their step number 1 is going to be modeling the gas transport without the reaction, just how any gas or multi-gases will flow in the soil. So we use a finite element analysis. We made the discretization using the Galerkin method. And we, for the governing equation, we used mass conservation combined with Darcy's and Fick's law for advective and diffusive law, respectively. So we have this will be the finite element equation, and then we basically have the solution for the change on concentration. The C here will be the concentration, is the variable we are solving for, and then we have this term that is going to be flow advection, is how is the gas flowing into the soil because of different pressures. And also we have the diffusion, how is the gas flowing into the soil because of difference on concentrations, and all that based in some boundary conditions. Basically, how much input and output of gas I have. We made the verification of this method with analytical solution, and as we can see, we see the blue line, and it matches pretty good with the analytical solution. What make us think that we already have the model in the program for modeling gas transport. With that done, we go ahead and can include the carbon reaction. So the reaction is going to be the carbonation. It's going to be an extra term about the consumption of the CO2, how the CO2 is changing because we are creating this binder of calcium carbonate into the system, and all the other terms remain the same. This is going to be a source term, and we have to take care of that term. For that, we will use the Papadakis equation is a linear equation that will depend on how much lime we have in the system, how much CO2 we have in the system, but also it will depend on how much water we have in the system and this coefficient of carbonation reaction. So the coefficient of carbonation reaction is how fast we are creating the calcium carbonate when the CO2 is being consumed, right? So at this point of the presentation, we have this program that is going to be a finite element method. The pre-processing is going to be like the geometry, the mesh, and all the conditions, the boundary conditions is going to be from a problem type or from GID. That is a program just for pre-processing in this case. And then from that, we can execute the code using MATLAB, the finite element code, and then the output, we can visualize it in ParaView. So I'm providing an example here. We are going to simulate a 1D carbonation. So the CO2 is coming into the system, and I have already the soil with lime and some saturation. And we are opening the bottom boundary conditions. So as you can see, the total pressure, it will accelerate in the system. The CO2 pressure, the CO2 is going to advance into the system. And as the CO2 is advancing, the calcium carbonate or the binder is being created. And then, all right, at this point, we have the model. It can recreate the carbonation, but we need to know if this is working. So we need to know the calibration. For the calibration, we have laboratory set up for the calibration of the K sub I parameter. So it's going to be a column of soil. It has pressure meters for measuring how is the pressure changing in the column of soil. We have flow meters for measuring how is the flow changing coming into and going out to the system. How is the wave velocity changing with these bender elements on the soil? And then how is the CO2 advancing with this thermal camera? Because it's an exothermic reaction, it will increase temperature and we can capture it. Something like this. And then we can respond to some question like, how is the CO2 front advancing with this? How is the pressure changing with the pressure meters? How is the flow rate changing with the flow meters? How is the shear wave velocity changing with the bender element? And then what is the efficiency of the reaction? We can take the sample after and see see how much calcium carbonate is in that sample. All that as a function of the density, the water content, and the lime content. So this is it for now. The future work will be after we finish this stage of the lab work, we can calibrate the model and hopefully we can recreate some like large scale experiments and hopefully in the future this can be a tool for soil carbonation. And thank you so much for watching this video.